Hey guys, Mr. Breen here, and in this video I'm going to be talking about the basics of game theory. So what counts as a game? Well, a game has to have a few different things. First of all, a game has to have two or more players. If you only have one player, it's not really a game. Second of all, a game has to have several different actions that those players could perform. Third, we have to know what information is available to those players when they're making those actions, when they're taking those actions, making those decisions. And fourth, those actions that they take have to have payoffs when you consider what everyone does. Let's take the following very simple game. So there's you and your brother, those are the players, and you can whine or not whine. Okay, those are the possible actions you could take. You know when your brother is going to whine, and you know when you're going to whine, right? So that's the information you have. If your brother starts whining, you know that. And the payoffs are, well, you are deciding how to split 5 cookies. There are only 5 cookies. There's never going to be more or less than 5 cookies. Those cookies will be distributed between you and your brother somehow. And you're trying to get as much as you possibly can. Now this is called a zero-sum game, because no matter what you do, or no matter what your brother does, there's always going to be just 5 cookies, no more and no less. That also means that for every cookie you get, your brother doesn't get that cookie, and for every cookie your brother gets, you don't get that cookie. Now let me explain my notation here. So I've set up this little matrix, and the number inside the boxes is how many cookies you're going to get under these circumstances. So if you whine and your brother whines, you get 3 cookies. If you don't whine and your brother does whine, you're not going to get any. He gets them all. If you don't whine and your brother doesn't whine, you get 2 cookies. And if your brother doesn't whine, but you do, you're going to get all of the cookies. Now there's something very important about this decision. Your brother can actually wait to see what you do before he decides what he's going to do, and you can wait to see what he's going to do before you decide what you're going to do. In other words, if your brother starts to whine, you can start to whine after that. If your brother doesn't whine, you can see that and decide not to whine or whine whatever you want. And the same thing with him. If he sees you start to whine, he can start to whine if he wants, or he can decide not to whine. Now, under those conditions, what's going to happen here? Well, what should you do? Notice that no matter what your brother does, you're always better off whining than not whining. So if you whine and he whines, you get 3. And if you don't whine and he whines, you get 0. If you whine and he doesn't whine, you get 5. And if you don't whine and he doesn't whine, you get 2. So you're always better off whining. Now, of course, you'd like to have all the cookies, okay, but you can't make him not whine. So what's going to happen here? Well, sort of an arms race. You're going to whine because you're always better off that way. And your brother, because he's much better off, if he knows you're going to whine, he's much better off whining than he is not whining. Because if he doesn't whine, you're going to get all the cookies. If he whines, he at least gets 2. Now here's another kind of zero-sum game. Let's say that there's a 2-point conversion situation, and the offense has to decide whether to run or pass, and the defense doesn't know what they're going to do, and they have to decide whether to defend mostly against the run or mostly against the pass. So again, I'll explain this notation. So if the offense decides to run the ball and the defense decides to defend against the run, then the offense only has a 30% chance of making it. Whereas if the offense decides to pass and the defense defended against the run, then there's a 90% chance that the 2-point conversion will be successful. And then if the offense decides to run and the defense decided to defend against the pass, the offense has a 95% chance of success, whereas if the offense passes and the defense decided to defend against the pass, then there's a 40% chance that the 2-point conversion will be successful. Okay, this is a game because, again, you have 2 players. Each player has certain actions that they can take. The payoff is the percent chance of success. And the information that they have as well, they have to reveal their hands at exactly the same time. So the defense can't see what the offense is going to do ahead of time, and the offense can't see what the defense is going to do ahead of time. Now, with this kind of game, it's harder to say exactly what ought to happen. You might say, well, the offense is best off if this happens. That's true, but they can't force the defense to have a pass defense, right? So You might say, well, okay, the offense will always run, or they will always pass because they at least get 40% chance of success, right? But if they always pass, then the defense will always have a pass defense and they'll only be limited to 40%, but they might be able to do better by every once in a while running, right? Because if the defense has a pass defense all the time and they run a few times, the running play is going to have a 95% chance of success. So assuming that they play this game over and over again, or the situation continues to come up, maybe they pass a lot and sometimes they run. Now, not all games are zero-sum games. Sometimes you can have a game where you have you and someone else, 2 players, and each of you has different choices that they can make. You can either choose left or right, and they can choose up or down. These are just abstract ideas here. And they have different payoffs for each of you. So you don't always necessarily lose when the other person gains, and the other person doesn't always lose when you gain. And we're going to measure the payoffs. These are the payoffs in these boxes. These are the payoffs measured in utils, or the amount of happiness you get, sort of an abstract measure of happiness. So more is better for you, right? So which should you choose here? Well, the first thing you might notice is that you're best off up in this box. So you might say, I'll choose left. But you should also notice that you're playing against someone else, and this is actually his worst box. So he definitely doesn't want, if you choose left, he doesn't want to choose up. If you choose left, he wants to choose down and get 6, which actually makes you worse off than any of your other possibilities. Now, I've forgotten another important aspect of the game, which is that you have to make this decision at exactly the same time as the other person, and you have to reveal your hands at exactly the same time. You can't wait to see what he's going to do before you decide, and he can't wait to see what you're going to do before he decides. So in figuring out what you should do, you might say, okay, if he chooses up, I'm better off choosing left, but if he chooses down, I'm better off choosing right. Well, now I'm kind of stuck. Unless, that is, I notice that he has a clear choice. All right, if you choose left, he's better off choosing down. And if you choose right, he's better off choosing down. So you might look at his decisions and say, well, he's always going to choose down, so I better choose right. Since he's always going to do this, well, am I better off with 2 or am I better off with 3? Well, I'm better off with 3, so I'm always going to choose right. This box where I choose right, and this box where I choose right and you choose right and he chooses down, this is called an equilibrium. An equilibrium. And it's an equilibrium because nobody can make themselves better off by choosing something different. Notice if you choose left instead, if you move over here, then you're going to be worse off by 1. And if he chooses up, he's going to be worse off by 1. So you're going to just sit there. Now this assumes something else. This assumes that you can't negotiate with each other. What is the most efficient outcome for all of society? Well, up here, the total amount of utility is 11. Here it's 7, here it's 8, and here it's 8. Clearly, this is the one that should be chosen, but this is the equilibrium. So what if you could negotiate with each other and trade? Well, in that case, you might say, look, you choose up, and I'll choose left, and we'll end up here, and yes, I'll be better off, but I'll trade you some. How much are you going to trade? Well, you have to make him better off than he would be at the other equilibrium. So you have to trade him at least 4, right? Because he's going to have 1, and you have to trade him actually probably a little more than 4. So if you trade him 4.5 of what you have, then he's going to end up at 5.5, and you're going to end up at 5.5, and you're both better off. Now let's take a look at one of the all-time classic game theory dilemmas. And this is called the prisoner's dilemma. So you have 2 prisoners, they've committed a crime together. There's prisoner A and prisoner B. And these are their options. If both of them confess, they're each going to get 5 years in prison. If both of them keep quiet, they'll be brought up on lesser charges, and they'll each get a year in prison. If prisoner B keeps quiet, but prisoner A confesses, prisoner B will go to prison for 20 years, and prisoner A will not go to prison at all. If prisoner B confesses and prisoner A keeps quiet, prisoner B won't go to prison, but prisoner A will go for 20 years. Once again, this is not a zero-sum game, right? And the clearly efficient outcome for prisoner A and prisoner B together is to both keep quiet. But what's the equilibrium? if prisoner B looks at prisoner A's payoffs, he's going to notice that, look, if prisoner A confesses, he goes to prison for 5 years or 0. And if he keeps quiet, he goes to prison for 20 years if I confess, and 1 year if I keep quiet. So he's always better off confessing. So in that case, I better confess too. Okay? And prisoner A will notice the same thing. Look, prisoner B, if he confesses, he gets 5 years or 0, but if he keeps quiet, he's going to get 20 years if I confess and 1 year if I keep quiet. He's always better off confessing. So this is the equilibrium, even though this is the efficient outcome. Notice that this situation isn't made any better if prisoner B and prisoner A can talk to each other, because they might get together and say, okay, look, we're both going to keep quiet, right? Yeah, we're both going to keep quiet. But then if you separate them to make their decisions, even if you keep them together to make their decisions, either one is still better off confessing than keeping quiet. So that's a big problem. Anyway, I want to point out a few things. Notice that in my notation, prisoner A, the person on the sort of over here, right? This person's payoffs get listed first. Here it's a negative payoff, so you want to make it as low as possible. And the person whose decisions are on top up here, they're going to come on the right.